Started, and then people will hopefully start trickling back in. So the chair of the next session is Russ Tedrake.
Okay, hi everybody. Very excited for the next set of talks. We get a lot of, maybe if there's a theme to the session, it's a bit on tools, and I'm very much a fan of tools myself. We're going to get started right away here. We'll start with the first talk about Proxima from Daniel Rakita.
Great, thank you. So a collision proximity query in robotics is a scalar function denoted as C here that characterizes how close a robot is to either a self-collision or collision with obstacles in its environment. A common way to frame this function is to take the signed distance between all pairs of rigid shapes, map these distances through some loss function, then sum up all these values to get a single collision proximity output value. Many areas of robotics, like those listed here, rely on this kind of function, as well as its gradient, to generate motions that avoid or adapt to potential collisions. So a big question at this point is, how should this collision proximity function be computed? So culling approaches, such as bounding volume hierarchies, try to eliminate many unnecessary distance checks at runtime. These approaches still provide an exact result, but they have no efficiency guarantees, and in the worst case, may still need to perform distance checks between all pairs of shapes. Conversely, recent approaches have used supervised learning in order to train models that approximate proximity functions. These approaches have guaranteed efficiency as they just involve a single feed-forward pass through the model. However, the output value has no accuracy guarantees, and errors may be difficult to characterize or bound. In our work, we present a new approach for computing a collision proximity function for robot manipulators that formalizes a trade-off between efficiency and accuracy and provides an algorithm that gives control over it. Our algorithm, called Proxima, works in one of two ways. First, given a time budget as input, the algorithm returns an as accurate as possible proximity approximation value in this time. Or second, given an accuracy budget, the algorithm returns an as fast as possible proximity approximation value that is within the given accuracy bound. Further, both the time-budgeted and accuracy-budgeted versions of our algorithm are able to guarantee that the output value is a cautious approximation that is bounded from below by the ground truth value, meaning the safety of the robot or surrounding obstacles can be ensured in downstream applications. So how do we achieve all this? At a high level, our algorithm involves the following steps. First, the algorithm computes lower bounds on signed distance for all pairs of shapes. Our work proposes a novel way for computing these bounds in just a few nanoseconds each, making this step efficient even for scenes with hundreds of shapes. Next, the algorithm prunes any pairs of shapes with lower distance bounds that are too large to be included in the final output. The algorithm then computes guaranteed upper bounds on signed distance for the remaining pairs of shapes. Again, our work proposes a novel way for computing these upper bounds in just tens of nanoseconds each. These upper and lower bounds are interpolated to form an approximate distance for each remaining shape pair, and if the loss function used is monotonically non-increasing, we can also bound the maximum possible error that could come from each pair in the output sum. The algorithm sorts the pairs of shapes based on their maximum possible error from greatest to least, sums up an initial approximation value in maximum total error, then processes ground truth signed distance checks between pairs of shapes in sorted order until either time is up in the case of a time budget, or until the total possible error is below some given epsilon in the case of an accuracy budget. Because ground truth distance checks are processed in order of maximum possible loss function error, we argue that our algorithm makes great use of its computational resources within its allotted budget. So briefly looking at some results, we see that Proxima here with an accuracy budget of 0.5 is much more efficient as it requires many fewer expensive signed distance checks, all while having a cautious, comprehensible bounded error. Our paper shows that Proxima and its gradient can be incorporated into robot motion generation tools, such as this optimization-based inverse kinematic solver seen here. We show that Proxima affords highly interactive, collision-free motions even on this 66-dimensional humanoid robot. And here is another example where the humanoid is avoiding collisions with a dynamic environment obstacle, again using Proxima to afford a tight interactive computation loop. So we provide open source code that implements Proxima, so feel free to check that out. Thanks so much, and I'll take any questions after this session. Thanks.
Beautifully presented. Thank you very much. Our next speaker is Antoine Bambad from INRIA.
Hi, my name is Antoine Bambad. I'm a PhD student at INRIA and working at the interface between robotics and optimization. And I will present you, I'll present you ProxQP, which is a convex quadratic programming solver, which consists in minimizing a convex quadratic cost under linear constraints. And convex QP is a core modeling tool of robotics because it is involved in contact modeling for dynamics, inverse kinematics, and dynamics. And the problem is that today, QP solvers have trouble to be at the same time accurate, fast, and numerically robust. For example, IDMM algorithm has trouble to reach in a reasonable time solutions at a low accuracy. Interrupt methods cannot be easily warm started, which restrict them from control applications, and active set methods can be fast, but also they depend, they need strong assumptions to work well. Hopefully, another family of methods based on the augmented Lagrangian can match a priori all these specifications, and that's what has motivated our choice for designing a solver based on this approach. So the augmented Lagrangian is defined as the sum of the cost function and this difference of two squared norm term in blue. This merit function introduced by Esnes and Powell is the basis of the method of multiplier below, which we'll see below, and which can be used for solving the original QP problem. And the first term in blue constitutes a smooth penalization of the constraint with respect to a shift defined by the multiplier z. And the problem of this method is that xk is not guaranteed converging, which can be troublesome for some robotic application like in motion planning. Hopefully, Tyrrell Rockefeller has shown that by adding this proximal term in blue to the augmented Lagrangian, if one iterates the proximal method of multiplier below, then both xk and zk will converge as soon as there is a solution, which is really appealing, and the function phi is what he has called the proximal augmented Lagrangian. We have introduced one supplementary term to phi, so the blue one, which makes the function m depending both of x and z. And we have introduced this merit function because the linear systems involved for minimizing it are better conditioned than the one involved with the phi function. So our scheme is more robust and accurate. And minimizing this merit function enables solving also the original QP problem with the scheme below. But we are not limited to this algorithm because we have another contribution for accelerating it. So this minimization step is only the first step of PROX-QP. So here you can see PROX-QP algorithm. So once we have found candidates for minimizing the M function, then the if-else condition in red is here for accelerating the scheme. It constitutes what is called the bound constraint Lagrangian algorithm introduced by Toin and al. For calibrating the mu parameter, which is the one calibrating the speed of the algorithm. So mixing the new merit function plus BCL is the second contribution of the algorithm. So the third contribution is that we have implemented ProxQP in C++ using Eigen library, and we have also re-implemented 3 specialized backends for dense, sparse, and very sparse and large matrices, which is, to the best of my knowledge, unique for a QP solver. And the solver will be open source with a BSD license, and the API will be close to the one of OSQP. So now we'll present you some benchmarks. So I've benchmarked ProxQP against OSQP on inverse kinematics and dynamic tasks. And we have seen that ProxQP is about 6 to 9 times quicker than OSQP. We have also made benchmarks on standard QP from the optimization community, and I've seen that ProxQP is also always the quickest. For example, for a QP with 1,000 variable, ProxQP is about 10 times quicker than OSQP. Yeah. And so on this slide, you can see performance profiles on a subset of very hard QP from the optimization community, so Maros Mezzaro's repository. And so on the ordinate, you can see a performance ratio, a ratio of problem solved with respect to a performance ratio, measuring how slow a solver is with respect to the best solver solving all these percentage of problems. So the higher the better, and you can see that ProxQP is always above all other solvers. So I've introduced you ProxQP, which is a fast, robust, accurate open source solver based on a new augmented Lagrangian algorithm, combining a new merit function and a globalization strategy for speeding it up. And I'll be happy to discuss with you more on it on the poster session, the sixth poster, and thank you very much for your attention.
Okay, excellent. Our next talk is from Skydio. Heike from Skydio is going to present SymForce.
Yeah, hello. So we present SymForce, an open source library for fast symbolic computation, code generation, and nonlinear optimization for robotics. This is work from the Skydio autonomy team. So SymForce is made for writing algorithmic code for tasks like SLAM, MPC, calibration, bundle adjustment, and controls. Compared to alternatives, it results in faster runtime performance, faster development cycles, and fewer lines of code to maintain. SymForce powers tens of thousands of autonomous robots at Skydio. So the primary workflow consists of 3 stages: symbolic math, code generation, and optimization. First, the problem is modeled in Python with the SymPy API extended to include geometry types, camera models, and Lie group calculus. Second, symbolic functions are introspected to auto-generate highly performant runtime functions. And third, generated functions are used in our tangent space optimizer. So let's walk through this simple example where a robot moving through a 2D plane has noisy measurements for a distance sensor and bearing to known landmarks in the scene. To begin, we model with a residual function for each of the sensor measurements. These functions output symbolic expressions which can be explored, analyzed, and manipulated for rapid development. The top function computes the residual for distance traveled, and the bottom for bearing angle to the landmark. So we pass each function to the code generation class and tell it what language to generate, in this case C++. We get a generated C++ function with an equivalent API to the symbolic function. It has no branches, memory allocation, and its only dependency is the eigenmatrix library. By changing one argument, we can generate an equivalent Python runtime function that depends only on NumPy. SymForce aims to support many target languages. With one more function call, we can automatically generate tangent space Jacobians or Gauss-Newton linearization with respect to any of the function arguments. And finally, we can construct a factor graph from the generated residual functions and derivatives at each time step, create initial values, and invoke the optimizer from Python. And the same optimizer API is supported in C++ once the user is ready for production use. So here we see the problem being optimized. This overall workflow scales well to a wide range of complex problems up to hundreds of thousands of operations. And SymForce's code generator is broadly useful even without the optimizer. So as we saw, SymForce does not require any handwritten derivatives, which tend to be among the most error-prone tasks in robotics. SymForce introduces a novel method to automatically compute tangent space Jacobians of functions that operate on Lie groups, like rotations and poses. All a user needs to do is create a symbolic expression and call the Jacobian function as shown here. SymForce introduces a technique to avoid singularity points without introducing branching using an infinitesimal variable epsilon. For example, this strategy can create a branchless expression for sine of x over x without a singularity at the origin. Handling this correctly is key for robust behavior. And the largest advantage of SymForce is speed. SymForce generates highly performant code by operating on the fine-grained structure of a computational task to avoid unnecessary work. SymForce functions are flattened into a chain of instructions that share all common subexpressions, leverage sparsity, and avoid branching. So let's take as an example computing the product of x and y, the matrices shown here. Similar tasks are common when dealing with 3D transformations or applying the chain rule during automatic differentiation. So naively computing x, y, and their dense product requires 417 operations. SymForce's generated expression, as shown here, requires only 34 operations. SymForce generates output entries directly with no overhead because it knows the exact sparsity patterns from the symbolic code. In contrast, using sparse matrix multiplication at runtime is slow because it requires dynamic memory allocation. In addition, SymForce is much more powerful at common subexpression elimination than a compiler because it can flatten and share terms across arbitrary symbolic function boundaries. So we profile this task for a wide range of matrix sizes and sparsity patterns from the sweet sparse collection. SymForce outperforms the best of eigen in C++, sparse or dense, by 4.8x on an Intel CPU and 7.1x on an NVIDIA Tegra CPU. Next, we measure the linearization time of a robot localization problem with 5 poses and 20 landmarks, implemented idiomatically in SymForce, GTSAM series, and JAX. We generate 2 SymForce formulations, a fixed size problem that is faster and a dynamic size problem that is more flexible. SymForce fixed outperforms the best non-SymForce result GTSAM by about 5x on both Intel and Tegra platforms. SymForce dynamic outperforms by about 2x. So please visit our repository or pip install to get started with SymForce. Thank you, and we hope our contribution can benefit many of you.
Okay, very nice. Our next speaker is Yash from NVIDIA, who's going to tell us about Factory. No? Oh, sorry, David Snyder, my bad. My bad. David Snyder from Princeton is going to talk to us.
Hello, everyone. My name is, I guess I'll jump right in. So our motivation for our work on failure detection is that many systems, including simple ones, can have unexpected failure modes. On some of these may be innocuous, but on the other hand, we see that on the right, an autonomous vehicle may mistake something like the moon for a yellow light. And more generally, we know that learned systems that use black box policies, including possibly humans, can fail catastrophically in novel environments. And so our goal is to provably predict failures in these environments. So we use for our problem formulation the motivating example of drone navigation. We assume we have access to an environment E. We do not know parameterization of E, of the distribution that E is drawn from. Instead, we access it through a sample S of n IID environments from DE. We don't make assumptions about the underlying dynamics. They could be nonlinear or hybrid. We allow for rich sensing, e.g. camera images, and we assume an arbitrary black box task policy mapping the observations to actions. And so for this framework then, the intuition for how we will then perform failure prediction is as follows. We will assume that we can run the policy pi in any of the environments, and then from this we will get an observation history and a true label, determining whether or not the controller truly succeeds or fails in the environment. From this, we can run the failure predictor online to generate predictions of failure. And then the cost for this then is structured as follows to act over the course of the entire trajectory. We have that if the trajectory is truly a failure, it must predict failure before the failure occurs. And if it never predicts, if it's a success, it must never predict failure. In each case, there's a cost of 1 otherwise. So this is a setup to allow us to run online while having a cost over the whole trajectory. So in order to then generate bounds or safety guarantees, we need to train on the environments drawn just from S, but we need to generalize to the unseen environments in the distribution DE. So we'll use Pack-Bayes bounds that say essentially that with high probability, the true cost of a failure predictor generalizing to DE is bounded by the training cost plus a regularizer term. So then the intuition is that in order to get a good failure predictor that generalizes, we need to optimize the right-hand side of the above equation. However, this runs into a slight hitch, which is that if we assume that we have a good policy with a low failure rate, most of the training example will be successes, and the error won't depend on the actual failures that we want to classify. So in order to get around this, we motivate a class conditional Pack-Bayes bound in which we minimize the conditional error rates, and then this helps us control for the bias towards the more common class. So we show here an example for drone navigation, which we'll discuss in the experiments, where we see the true performance in blue and then the bound in red for minimizing varying weights of the conditional errors. For the first experiment, we use drone navigation. We have correct predictions in the top right and bottom left. And then we have an overly conservative error in the top left, where we stop a case where it doesn't actually fail. There were, importantly, no false negatives during test time, so we have a relatively conservative behavior. So for this experiment, the controller succeeded about 75% of the environments, as shown in the top row. our misclassification bound for trajectories was on the order of about 12%, so we have reduced the number of costly failures by at least a factor of 2. This bound is validated both in simulation and on real environments drawn again from this distribution, as you can see in the last 2 rows here. The second example we use is vision-based grasping amidst clutter. So here the robot is tasked with grasping a mug. Similar to before, we have the correct classifications in the top right and bottom left with an overly conservative misclassification in the top left. And again, no failures were observed at test time for this setup. So the results are similar, presented similarly to before, except we have 2 different controllers with varying degrees of performance, as shown in the top row. Again, the misclassification bound is able to meaningfully reduce the number of failures observed in testing. And then we're able to we validate these bounds again in simulation and on real experiments in the future. So in summary, we present pack-based failure prediction to provably improve safety online. The bounds are computable, interpretable, and they're policy agnostic, task relevant, and they apply to systems with arbitrary dynamics, high dimensional sensing, unknown measurement of the environment. So for more details, please see our poster and see our paper, which is linked. Thank you so much.
Okay, now for Yash from NVIDIA, the final talk before our Q&A, so get your questions ready.
I'll present Factory, a collaboration between NVIDIA, robotics, and simulation. We have 3 primary contributions. The first is methods for fast, accurate, robust simulation of contact-rich interactions developed in PhysX. The second is robot learning tools for robotic assembly, provided in Isaac Gym. And the third is proof-of-concept RL policies for assembly developed in Isaac Gym. I'll now discuss our methods for simulating contact-rich interactions. We synthesized sign distance field collisions, a contact reduction scheme, and a Gauss-Seidel solver to achieve our results. Rather than representing objects as convexes or meshes exclusively, we also represent them as sign distance fields. We compute the SDF for an object on a dense voxel grid and collide the mesh of an opposing object against this SDF. A canonical problem in contact simulation is simulating a nut and bolt assembly. And using SDF collisions, we were finally able to do this in real time. But SDFs are not all that you need. In robotics and RL, you may want to simulate hundreds of thousands of environments at the same time. But for a single M4 nut and bolt, you may generate 16,000 contacts. With a Jacobi solver, due to memory bandwidth limitations, you may only be able to simulate 20 nuts and bolts at the same time. And an inherently serial Gauss-Seidel solver would be unfeasibly slow. Thus, we implemented a contact reduction scheme. First, we generate candidate contacts using SDF collisions. Then we assign these contacts to existing contact patches based on the similarity of their normals. And for any unassigned contacts, we select the deepest ones and generate new contact patches. And we reduce contacts within patches using similar methods. Using this scheme, we can reduce 16K contacts to just 300. A Gauss-Seidel solver is now feasible, and we can simulate a theoretical maximum of 35,000 nuts and bolts. Here's a simulation of 1,000 nuts and bolts in real time. This is effectively a 20,000 times speedup over the state of the art. We also tested the simulator on 7 other challenging test scenes. Here are 512 bowls falling in the same environment. And for some reason, this video went viral. And here is a vibratory feeder mechanism actually vibrating at 60 hertz. And the Franca picks up a nut and tightens it onto a bolt, and we're able to simulate 128 of these in real time. I'll now discuss our robot learning tools, which consist of part models, robotic manipulation environments, and controllers in Isaac Gym. We provide 60 high-quality part models that were designed based on international standards or designs sourced directly from manufacturers. This includes all rigid parts on the NIST task board, as well as dimensional variations. We also provide 3 robotic manipulation environments for planing, control, and RL. This includes the nut-bolt environment, which includes a Franca robot and a nut-bolt subassembly, an insertion environment, which includes insertion assets such as electrical connectors and pegs and holes from the NIST board, and a gears environment, which includes the gears subassembly from the NIST board. We also implement 7 tensorized controllers, and the RL agents in our framework can be formulated to use their action spaces as targets to any of these controllers. Finally, I'll talk about our proof of concept RL policies. We use our simulator, assets, environments, and controllers to demonstrate that we can perform multi-step assembly procedures using data-hungry on-policy algorithms, but very efficiently. So we focus on the case study of nut and bolt assembly, and we decompose the problem into 3 phases: pick, place, and screw. We train a sub-policy for each, and then address policy chaining. So out of the 3 sub-policies, the screw sub-policy was by far the most difficult to train. It was replete with numerous pathologies that one might also expect to see in the real world. As a result, we did a systematic exploration of observation spaces, action spaces, controllers and gains, and reward formulations, and ultimately we were able to achieve an 85.6% success rate. We then focused on sequential execution of these sub-policies. We used a very simple policy chaining scheme whereby the output states of policy n were used to define the randomization bounds of the input states of policy n+1 during training. And we achieved successful execution of pick, place, and screw in sequence. Finally, we compared contact forces generated during simulation execution of the screw sub-policy against a real-world human data set for the same task. We found that the histograms were essentially very well aligned. Thank you very much. The factory code is being officially released today, and we're really excited to see what you do with it. Thank you.
Okay, thank you very much. So I have all the speakers come back up. I'll take the right to ask the first question, I guess, here. So for the factory talk, since we just heard it, so I guess the contact reduction was a big part of your performance improvement. And I know PGS is standard concern. The standard concern with the projected Gauss-Seidel is accuracy. So I wonder, did you ever do any metrics, for instance, on when you went from 16K down to 300 contacts, what's your maximum penetration on the 16K contacts? What were your kind of, did you have an energy dissipation budget? Did you check the accuracy of your reduction?
No, this is a great question. We didn't actually explicitly evaluate maximum penetration depth. I think it's an important thing that we should do. We should provide these maybe tables that can actually evaluate that. We also use TGS rather than PGS, okay. So temporal Gauss-Seidel, which has sort of accuracy improvements relative to PGS. Maybe some of those concerns will be alleviated.
Excellent. Okay, I see a question over here.
Yes, I have a question regarding to the failure prediction with statistical analysis. Yes, just wondering, what's the time, how much earlier can you predict the failure, or can you tune about it?
I'm sorry, could you repeat the last part of that really quickly?
So how much earlier can you predict for the possible failure, and can you somehow tune this horizon? Like basically, we can predict this failure earlier or sooner, or something like this.
Oh, that's a really good question. For the setup that we used, we only penalized as long as it was predicted beforehand. You could see in one of the experiments, like the drone, for example, had time to react in order to not hit the obstacles. I think there are ways you can modify the cost function, for example, so you could make it sort of scale with the amount of time in advance that you predict. I think the trade-offs are that the earlier you do it, perhaps, the less information you allow yourself to gather. It's maybe, maybe you look ahead and you see a lot of obstacles, then you see later there's a gap that you actually can go through. But it is tunable, yes.
I see. And another question is, like, in control theory, there's a lot of work done in reachability analysis. Like, have you considered that?
Yes. I think we were thinking of this as being, in some ways, complementary in that we rely on fundamentally different assumptions. And so we, for example, don't need as much, perhaps, if you will, sort of knowledge about the fundamental system dynamics, the noise, what have you. We allow the system to sort of behave so as it is. So we do have to assume stronger things about the environments not being, say, adversarial in order to do this. So I think they're kind of complementary type guarantees. Yeah.
I see. Thank you. Great topic, by the way.
Thank you.
Okay, it looks like we've got another one at the same microphone.
Yeah. Hello. My question is for SymForce. How do you guys handle constraints in optimization problems?
Yeah, so the question is about constraints.
Yeah.
So right now, the SymForce optimizer itself doesn't do hard constraints, although that's something that we plan to add. But we use soft constraints and barrier functions. And I'll also just note that, you can use the SymForce symbolic math and code generation and easily integrate that with any other solver, for example, PROX-QP or any other optimization library you're already using by generating runtime functions and plugging them in.
Okay, thank you.
We have somebody up on the balcony that's going to ask a question. Get the microphone.
Hi, I have a question for the SymForce team. When you generate the C++ code from the Python code, how interpretable is it by a person? Like, could I read through the C++ code and understand it, or is it effectively treated almost like a black box in Sky?
Yeah, great question. So if you generate a function, the thing that's very interpretable is the interface. So that'll match argument for argument with your Python function, including kind of runtime versions of the geometry types and an eigen, dense, or sparse matrix and so on. And the outputs. The inside of the function will have a series of kind of intermediate terms and then output results. And those, they won't be very interpretable at all, although you can look at the code. If it's a short function, you can, trace it out, but it's not, it's really a flattened version of what could have been many symbolic functions from different modules, and so it's not readily interpretable as a human.
Thank you.
Told one more question, sorry, Eric, but last question.
Yeah, I have a question for David, the one on vision-based control. So now it looks like the obstacles were more or less at the same distance in all these scenarios. What happens if you have more variability in terms of the distance to the drone?
Sorry, just to repeat the question, it's about the distribution over the obstacles for the drone navigation example?
Yeah, so now it looks that they are always at the same distance, and you vary a little bit the position. What happens if you have more variability in the distance to the drone?
Right. So I guess there are maybe two sort of answers to that. One is it would mean in some sense you're in a different distribution, so you might have to deal with bounds for distributional shift. In terms of our particular choice, we were trying to generate examples where, we were trying to create a distribution where we, I think, believed that there would be some feasible options, in part because we just didn't want to drive the drone into too many obstacles too many times. In that sense, I think we tried to make sure that there was many of the things would be feasible, but varying degrees of gaps or what have you. So you may have seen the false negative rate. There was a very tight gap that it was trying to go through, and the gaps were a bit tighter there. In general, I think the main thing is whether or not there's a distribution versus an adversarial type setting is better for the problem at hand. Yeah.
Okay, let's thank these speakers again. Okay. We'll move on to the next 4 talks before our keynote here. The first one is from Louis, who's going to tell us about contact detection from a convex optimization perspective.
Hello everyone, my name is Louis, and I will be talking about collision detection accelerated and optimization perspective. So collision detection is a fundamental problem in many robotics applications, such as optimal control, reinforcement learning, motion planning, but also in fields such as computer graphics. And basically, given 2 convex shapes, we want to compute the distance that separates them. Since we spend more time than ever inside the simulation, we need every fundamental algorithm to be as fast as possible, and that includes collision detection, for which we can encounter millions to billions of collision detection problems. And so for the specific problem of collision detection or distance computation, the JGK algorithm was designed back in 1988 and is still state-of-the-art today. It's named after its authors, Gilbert, Johnson, and Kearsley. And the beautiful idea of JGK is that computing the distance between the 2 shapes is equivalent to computing the point of minimum norm inside their Minkowski difference, which is the set in gray. And although the sub-operations of JGK have been improved over the years, The algorithm itself has remained unchanged and is often presented as a computational geometry algorithm. And we argue that in order to better understand it and to accelerate it, we must view at the problem through the lens of mathematical optimization. And at its core, as explained by the authors of JGK, the JGK algorithm is an instance of the Frank-Wolf algorithm, which was designed in 1956 and is one of the oldest and most studied method for convex constraint optimization. It can be understood intuitively as gradient descent modified to stay inside the convex set D. Basically, at each iteration of Frank-Wolf, we compute a support point by solving a simple linear subproblem. And after computing this support point, we move toward it, and by repeating this scheme over and over, we get closer and closer to the optimal solution we're looking for. And the computation of the support point on the Minkowski difference is very easy to do, as it can be decomposed back onto the original shapes. The problem with Frank-Wolf is that it zigzags, and to deal with that zigzagging, many solutions have been proposed over the years, and in this work, we focus on two of these accelerations for maximal computational efficiency. The first one is the so-called Nesterov-accelerated Frank-Wolf algorithm, which is a recent work by Li et al., in which the authors modify the Nesterov acceleration of gradient descent to suit it to the Frank-Wolf setup. And intuitively, the authors add inertia to the gradient, which generates a different sequence of support points, which hopefully reaches the optimal solution faster. Now, the second acceleration of Frank-Wolf is in this talk is the so-called fully corrective Frank-Wolf algorithm, in which we try to identify the optimal active set, so the optimal set of support points, which describe the convex combination as fast, the optimal solution as fast as possible, as a convex combination of them. And it turns out that you only need simplexes to describe the optimal solution. So, and simplexes are very computationally efficient to work with because there are a minimal set of points. So if you take the fully corrective algorithm and you restrict yourself to simplexes, as we show, you get the JGK algorithm. So to accelerate collision detection, we designed the Nesterov-accelerated JGK algorithm, which uses the two previously accelerations I just mentioned. So we use JGK as a base, and we add the Nesterov acceleration, which only really adds 2 lines of code. So it's a very simple addition. And we also design a simple heuristic for meshes, which are especially important in robotics, which gives us better performances in practice. But the Nesterov acceleration is the star of the show, and it's, even though the heuristic is here for meshes, it's basically the same thing. So we evaluate our method, Nesterov accelerated JGK, against JGK on 2 very large benchmarks. One is made of ellipsoid, the other one is made of meshes, as you can see here. So for this mesh benchmark, we took thousands of shapes of shape nets, and we generated millions of collision problems. And our results show that both in terms of number of iterations and in terms of timings, Nesterov accelerated JGK is up to 2 times faster than JGK, and that's especially true for when the shapes are in proximity or shallowly overlapping, which are 2 very important cases in physics simulation, especially when you're doing contact simulation, for example. So finally, Nesterov accelerated JGK is already implemented inside HPP-FCL, which is a fork of the FCL library. And HPP-FCL is used inside the Pinocchio robotics framework. But you can also implement this Nesterov acceleration inside of your own JGK implementations, as again, it takes only a few lines to do so. Finally, I'm poster 10, so I will happily see you at the poster session. Thank you very much.
Excellent talk. Thank you very much. So we'll have Vincent from Princeton come and tell us about failure, fundamental performance limits this time. Yes.
Thank you. I'll be presenting our paper on fundamental performance limits for sensor-based control and policy learning. So problems in robotics often reduce to finding the right mapping between pixels or sensor observations to motor torques. However, it's not always clear what sensor observations we need to find the right motor torques for our task. A recent example of this is the ongoing debate between Waymo and Tesla, where Tesla insists that they only need cameras to get safe and performant self-driving cars, whereas Waymo uses a multimodal sensor suite to achieve this task. And so this raises the question of whether both of these methodologies are equivalent, or stated otherwise, whether or not there's a fundamental limit on the safety and performance that can be achieved with cameras only. So we attempt to address this in our paper by proposing a fundamental limit for robotic control, where we consider a partially observable Markov decision process, and our goal is to find an upper bound that is independent of how the policy is implemented on the closed loop reward achievable by your controller, regardless of how your controller is implemented. It could be via MPC or reinforcement learning or some other method. And to do this, we introduce a new quantity that we refer to as the task relevant information potential, or TRIP. And the definition of this quantity is a little bit too complicated to fit into a 5-minute talk, but it is a function of the mutual information between the robot state and observation, and also the optimal closed loop, or the optimal open loop reward achievable on a given task. And importantly, the trip is monotonic in both of these quantities, which captures the intuition that, if the task is either easy to perform in the open loop setting, then you can achieve better performance, or in the case where moving forward. So the trip provides an upper bound for single step problems, and we can leverage this bound recursively to derive to get a bound on multi-step problems using dynamic programming. In our examples that are coming up, it's important to note that we are restricted to a finite action space for numerical reasons only. Our bound is independent of that, but however, the theory is independent of that. So for our first example, we consider a POMDP problem that's a common benchmark that admits a good open loop solution. So the robot needs to move to the goal state without falling into the lava, and there is a safe open loop policy that it can take where it simply moves left, either directly reaching the goal, or it will bump into the wall and then it can move right to the goal. However, the robot is equipped with a noisy sensor that gives a correct state reading with probability p correct, and it can use that information to achieve a better performance. And so we plot our bound versus the optimal POMDP solution and see that we get a fairly close correspondence between the two. In our next example, we consider a ball catching problem where we implement a MPC policy that selects between various trajectories for the robot. And in this case, the robot receives a noisy estimate of the ball's location with different noise scales. And here the state and observation space are both continuous. Again, we see a close match between the two. In our final example, we consider a motion planning problem where the robot is equipped with a LiDAR, and it needs to identify a path that will navigate it safely around the obstacles. And the LiDAR has multiple failure modes and different noise scales. And again, we evaluate our trip bound as we vary the noise scale and see that our bound, it matches the performance well. And in the last case, the policy that we were comparing against was a learned neural network policy. And to conclude, I want to mention some future directions that we're looking at. The most direct is to use our bound to compare different classes of sensors for robot tasks. We would also like to modify our algorithm to be amenable to continuous action spaces as well. A much more interesting extension is to apply this bound to robust control by considering fundamental limits on the performance of an adversary, and then trying to minimize the performance of the adversary so that we can generate a large reward with a guarantee. And finally, we'd like to try and derive similar fundamental limits for other important quantities in robotics, like memory or computation.
Okay, next we have Charles Dawson from MIT. He's going to talk about robot design optimization.
All right, thank you. As Russ said, my name is Charles Dawson, and it's my honor to be here as part of this fantastic program. Today I'd like to talk about how advances in programming languages, particularly automatic differentiation, can be used to improve the experience of designing and verifying robotic systems. To motivate this talk, I'd like to start by thinking about how engineering design happens in other disciplines. For example, both mechanical engineers and electrical engineers can make use of automated or semi-automated computational design aids to be more productive during the design process. This begs the question of what tools are available to us as roboticists to accelerate our design process. Clearly, robots are more than the sum of their hardware, mechanical, and electrical parts, so we need to think about what new computational design aids are appropriate for the robotics task. Our key insight in this paper is that if we can model a robotic system, both its software and its hardware, through a simulator, which is itself a computer program, we can use program analysis techniques like automatic differentiation to improve the process of designing and verifying that system. This idea of using automatic differentiation in the design process is not itself new, but our new take on it in this paper is that we can look at the full stack autonomous system from planning all the way down to control, and we look at the entire robot design process to come up with a framework that uses automatic differentiation in the process of design. At a high level, we like to think about this sketch of the robot design process. This starts with high-level design in problem definition and architecture selection, where the designer needs to think about what task they want to solve and what robotic system they're going to use to solve that task. And then it proceeds to a lower level, where the designer needs to optimize their given architecture and then verify that their design will achieve the desired amount of performance. The important distinction between these two levels is that a lot of the creativity in the design process happens at the higher level in problem definition and architecture selection, where the designer needs to specify things like the objective and what parts of the robotic system are subject to optimization. To go through a concrete example, we can consider this case where the designer wishes to use two robots to collaboratively manipulate a large box. Here in the problem definition phase, the designer needs to specify an objective, say get the box as close as possible to its target, and they need to specify some assumptions about the environment, such as making assumptions about the distribution of parameters like coefficients of friction. Then we need to move into the architecture selection phase, where we need to think about what sort of robotic system is appropriate to solve this design problem. And this involves specifying which parameters are open to optimization. In this case, we already said we're going to use two autonomous ground robots, but we might say that we want to use a neural network path planner to choose what paths those robots are going to follow, and then a feedback controller for tracking that trajectory. We don't need to know at this point what the exact parameters of that system, of those subsystems is going to be. We just need to sketch out the design in enough detail that we can implement a simulator to model its behavior. Once we have that simulator, we can use program analysis techniques like automatic differentiation to invert that simulator. You can use your favorite gradient-based optimization method to modify the design parameters to achieve the best performance. We also include a couple of different domain randomization and variance reduction techniques at this step to achieve better performance. And here we can see that the initial design with random parameters on the left does not get the box, which is the open outline close to its target position, whereas in the optimized design, it can get pretty close. Once you have an optimized design in hand, the next question becomes, how do you verify that design? How can you be sure that your design will achieve the desired level of performance? There are two sub-questions that we can consider within this topic of verification, and specifically in the context of our statistical method for verification. The first is what is our expected worst-case performance of a design? And the second is what is the sensitivity of that design to changes in the environmental parameters? For instance, our coefficients of friction in the simulation can't be perfect, so how much would we expect the performance to degrade if those parameters were to change? We answer both of these questions through the lens of extreme value theory and statistics. And there's a lot of nuance that I'd love to get into, but don't have time for this talk, so please ask a question in the Q&A or come up to the poster session. I think we're poster number 12. A natural question here is that if we're relying so heavily on simulation for designing and verifying a robotic system, what about the sim-to-real gap? Well, the anecdotal and empirical answer to that is that in our case, due to our domain randomization and variance reduction techniques, we find that the gap is not very large at all. Even with the rich contact dynamics in this pushing case, we were able to transfer without any further tuning or any system identification at all. I'd like to close both with these contributions and with a request, which is that if any of you are working on a challenging design optimization problem in robotics, and I'm sure many of you in this audience are, I'd love to hear about it. Please come up to me at the poster session, and I'd love to have a conversation about how we can use our framework to accelerate your design and verification process.
Okay, our last talk for the session is Ciro Moreno, who's going to talk about collocation methods for second-order systems.
So, our purpose with this talk is to show that the usual collocation methods for trajectory optimization are fundamentally flawed when applied to second-order dynamical systems like those in robotics. I will try to show you why and present our solution to this problem. To start with, let us recall the trajectory optimization problem. Suppose we have a robot for which we want to find an optimal trajectory Q of t minimizing a given cost function. This trajectory must fulfill some path and boundary constraints and satisfy the dynamics equation of the robot. To solve this problem numerically, a usual choice is to apply a collocation scheme. This consists in dividing the time domain into intervals and applying a quadratic rule to each interval to transcribe the continuous problem into a nonlinear programming one. This is done by imposing the constraints at a set of collocation points. The crucial part of this process is how to transcribe the continuous dynamics equation into its discrete counterpart, and this is the focus of our work. Usually, dynamics are described by a second-order differential equation, but usual collocation methods are designed for first-order systems with this form. So, to use these methods, in robotics, we typically reduce our problem to this form by defining the state vector x as qv and adding the constraint q dot equal to v. This results in this first-order system, which already has the form stated below. This reduction, which in the continuous domain is perfectly valid, leads to inconsistencies when the problem is discretized. In usual collocation, configuration and velocity trajectories are approximated using polynomials of the same degree, collocation equations for the slope q dot k to match the vk value at the collocation points. However, q dot of t will be a polynomial of a lower degree than v of t, so the two polynomials will not coincide. This yields an inconsistency between the q and v trajectories. Moreover, since the two curves do not coincide, the derivatives will be different too. In this case, their values will be different even at the collocation points because no constraint is imposing their coincidence. So we have that the collocation constraint imposes this condition, but we have that these two values are different, so the second-order dynamics equation is not satisfied at the collocation points. To solve these inconsistencies, in our approach, we directly impose the second-order dynamic constraint at the collocation points, and we impose q dot equal to v on the approximation polynomials. As a result, we obtain new versions of the trapezoidal and Hermite-Simpson collocation schemes that remove the inconsistencies and also present continuous accelerations. Here we see the collocation equations for the usual and new versions for such schemes. We can observe that the new equations are similar in complexity. The main difference is that usual scheme use the state variables in the same way, but in the new schemes, we have different collocation formulas for the q and v variables. To see how the new schemes compare to the usual ones in practice, we apply them to two benchmark problems from the literature, the carpal swing up and the 5-link bipedal walking problem. To measure the quality of the obtained solutions, we compute the second-order dynamic error, which is the integral of the residual of the dynamics equation. Here, we can see how this error decreases with the number of time intervals for the usual schemes. This is for the bipedal problem, but for the carpool, the plot is similar. Clearly, the Hermite-Simpson schemes shows a much lower error compared to the trapezoidal schemes. But when we switch to the new schemes, the error for each method is reduced in more than 1 or even 2 orders of magnitude, depending on the case. We can observe that this increase in accuracy doesn't come at the cost of additional running time, as new algorithms take about the same time as the usual counterparts to find a solution. So to wrap up, we can conclude that usual collocation methods yield inconsistent configuration and velocity trajectories, whereas the new methods we propose achieve trajectories with a much smaller dynamic error, satisfaction of the dynamic equation of the collocation points, consistency of the configuration and velocity trajectories, so less control effort will be required to track them, and continuous accelerations, which result in smoother trajectories, and all that without increasing the computational cost significantly. Thank you, and I hope to see you at poster number 13.
Okay, we'll ask everybody back up here again and have a few minutes for questions. Maybe I'll start, as, even though there's someone at the microphone, but this is my chance. Okay, so Vincent, so yes. I haven't thought enough about TRIP yet, but it sounds too good to be true. So I find myself trying to defeat it, right? Like, so the way you write, so the way I would think you would defeat it is if there's problems that are susceptible to memorization, for instance. Like if there's something that maybe, I think you guard against this with your open loop R in the mutual information, but what if there's something where if I get one bit of information that has a low mutual information with my state, but it's enough for me to flip in a memorized something? It seems like, it just seems fundamentally very hard to bound the performance in that kind of a setting.
Yeah, so I would be curious to see how it performs in that case, but I think that that would be compensated, like as you said, that would be compensated for by the relationship between the mutual information and the kind of like open loop case. I mean, that is somewhat. I guess that would be one step past the lava problem, because the lava problem you can solve without with zero information. But if you but you're right. I would be curious to see how it performs there, but yeah, the boundary accomplishment. I would say that the main way that, or I didn't have time to include this in the 5 minutes, but the other big assumption that we have is that the rewards are bounded. So if you have unbounded rewards, then the generalized Fano inequality, which is how we derive the trip bound, that doesn't really hold. So
that seems okay.
Yeah.
Good. Awesome. Thank you. There's a whole line of questions here.
Yeah, I have a question for Charles. So for the example you showed, it seems like the parameter search space is rather small. Have you looked into ways to use your framework for, like, for example, larger scale robotic system where you have more parameters to search, and then have you looked into ways to sort of like figure out the correct parameters to optimize?
Yeah, that's a great question. So in our paper, we use two main examples to demonstrate the capabilities of our system. The example that I showed on the slides here actually has several hundred parameters. It's a several layer fully connected network in planning, and then a number of trajectory feedback control gains. So I think several hundred is the upper limit that we've tested so far. The other example that we showed had far fewer parameters, but many more subsystems. So the other example in our paper is an autonomous navigation problem where you're optimizing the location of landmarks for sensor-based navigation. In that problem, we had more on the order of 10 parameters to optimize, but we had interactions between 5 or 6 independent subsystems that we wanted to optimize through. So I would say that the short answer is we've tried up to several hundred parameters. It performs well, and there are tweaks that you can do for automatic differentiation, forward or backward mode, depending on the relative number of parameters that you have.
All right. Thank you.
Hey, I also have a question for Vincent on the fundamental limits paper. So I wonder if you could comment on how tight the upper bound is. I think in your talk we saw as the noise level increases, the bound and the actual performance gap also widens.
So we don't have a theoretical quantification of how tight or loose the gap is at different noise levels, but it does it does seem that way in some examples, but not in others that we tried on. Yeah, so that would definitely be something to look at in an extension. But in general, we have found that the bound is, I guess, what I would call practically tight, and that it's not like totally vacuous in a lot of cases. So Yeah, so that's definitely something that I'd be interested in looking at for the next paper.
Cool, thank you.
I'm afraid we're only allowed one more question because we have to move on to the keynote. Sorry. Here we go.
I really like the idea of design and algorithm co-optimization. I'm wondering, how do we satisfy the physics constraint of designing a robot? Some parameters need to be physically plausible, right?
Yeah, that's a great question. So I think that at a high level, you can compare our optimization most directly to a single shooting optimization where the physics are baked into the simulation. So if you have hard constraints on the physics, we're not trying to satisfy those through collocation, for example, where we have those as hard constraints in the nature of the simulation. For parameters that you don't have full control over, our framework includes a distinction between design parameters, which might be like the weights of a neural network that you can freely change, or the mass of a link in your robot, and exogenous parameters or environmental parameters. So we include a method for handling these uncontrolled parameters in the environment. So in the example that I showed, the parameters that were uncontrolled included the mass of the box, the initial position of the box in the robots, and the coefficients of friction of all contact pairs. And those were assumed to vary according to various different distributions, either uniform or Gaussian. So we include the opportunity to bake in those uncontrolled parameters to our framework, because I think it's definitely important to account for what you can't control in the design process.
Thank you.
Okay, I hope you'll ask the rest of your questions at the poster session. Let's thank our speakers again.